Thank you so much for inviting me. I'm going to talk about a fun topic, essentially blockchain-inspired protocols where game theory meets cryptography. And if you have any questions, just unmute yourself and ask, and don't wait till the very end. I'm going to begin with the motivating example that comes from a true personal experience. I guess this is not uncommon in the crypto or in the theory community. Let's say you write a paper and you discover there's a concurrent work that has exactly the same result. So this happened to me a couple of times. Like, in fact, it happened to my first ever crypto paper when I was in grad school. And then it happened again in 2013. And this time the papers had exactly the same titles. Okay, so both papers were submitted to Eurocrypt 14, and then the program committee recommended the hard merge. So basically, we only got one presentation slot, and the challenging problem is, we have to decide one group to go and present the paper. I mean, of course, both groups were very eager to go present the paper, and we were, not geographically located in the same city. So how do we make this decision? A strawman solution, I guess, is for me and Shafi, who's a co-author on the other paper, to deal it out. But we want a more civil solution. So here's what we can do. We can run the coin toss protocol. In fact, this is what we actually did. Coin toss was actually first proposed in a groundbreaking work by Blum back in 1983. The way it works is the following. So imagine Shafi and we both pick a random coin, and we make a commitment of the coin, and we post the commitment to a public bulletin board. So in this case, let's imagine the blockchain is acting as the public bulletin board. Okay, so then after we both make the commitments, we open our commitments and reveal the underlying coin. And then we basically take the XR of the two openings, and the XR will be used to decide the winner. So in this case, our group had won the coin toss. Okay, so in this protocol, right, I may be concerned that Shafi is going to act maliciously, deviate from the protocol. Like, let's say maybe she has committed her coin, and then when I open my coin, she sees that she's going to lose anyway. So maybe she will refuse to cooperate and refuse to open her coin. So in this case, she basically aborts from the protocol. If she opens the coin wrongly, then it's equivalent to abort. So in this case, what do we do? I mean, it's pretty simple here, because you can just, in this case, Shafi basically is declared to have forfeited, and then I will win anyway. Okay. So this is a coin toss protocol. Typically for a coin toss protocol, we need two properties, right? So correctness is defined in the most natural manner. Basically, if both parties act honestly, the outcome must be a random coin. And we also need a fairness property. So how do we define fairness? In the standard line of work on multi-party computation in the crypto literature, so the de facto notion is actually very draconian. And it's a very strong notion that basically says, even if Shafi aborts, I must nonetheless still output an unbiased coin. So you can also call this unbiasability for this reason. But this very strong notion is unfortunately known to be impossible in a two-party setting, or in general in an n-party setting, when the majority of the parties can be colluding and corrupted. So this is actually due to a very well-known lower bound by Cleese. Okay, so now it may seem like I'm contradicting myself, right? So because there's a lower bound, so how can Blum's coin toss protocol even work? If you think about it more carefully, Blum's protocol actually achieves a strictly weaker notion of fairness. It's not completely unbiasable, right? In fact, if Shafi aborts, she can indeed bias the outcome. I mean, except that she's biasing the outcome not to her favor, but to my favor. Okay. So if you consider the players to be rational, right, and let's say they care about maximizing their own utility function, in this case, actually, it's easy to show Bloom's protocol satisfies a game-theoretic notion of fairness. In other words, the protocol is a Nash equilibrium, and Shafi's best strategy is just to play honestly, and honest behavior is the equilibrium. Okay, so that's very nice. And we know that Bloom's protocol achieves game-theoretic fairness in a two-party setting. And the next natural question to ask is, suppose we have n parties, can we still have game-theoretically secure coin toss? At this moment, it may not be completely clear what the formulation is for the n-party setting. I will explain that in just a little bit. So when we first started working on this question, we actually discovered to our surprise that this very natural question hasn't been considered at all in the literature. What's surprising is because initially the crypto line of work started with Bloom's protocol, which actually achieved a game theoretic notion of fairness, implicitly. But then the entire line of work on crypto switched to this very stringent unbiasability notion. Okay. So before going into more details, let me quickly mention that if we are willing to make some very strong assumptions, then there may be some trivial solutions. Like, let's say we are willing to assume honest majority, then we know in general we can have fair MPC with strong fairness in constant number of rounds. And this basically solves the coin toss problem as well, because coin toss is just a special case of general multi-party computation. But in decentralized blockchain applications, like honest majority is not necessarily a great assumption, because for instance, if you are playing a decentralized smart contract, oftentimes the pseudonyms are cheap to make up, and it could be 90% of the pseudonyms are actually controlled by the same party. Okay. Also, another trivial solution is kind of to assume the problem away, right? If you assume there's a trusted party who can toss the coin for you, then the problem goes away. Maybe the trusted party chooses some pseudorandom seed, then you can basically stretch the seed every time you need a new coin, but in this case, the coin would be predictable in advance. And we want the coin toss to be basically unpredictable. Okay, so let's refine the problem definition with this in mind. We are actually asking, right? So basically, assuming the coalition can be majority in size, and assuming no trust is set up, and basically in the plain model, can we achieve game theoretic fair multi-party coin toss? And if we can achieve this, then the next question to ask is the complexity. Like in the rest of the talk, I'm going to talk a lot about the round complexity of the protocol. Okay, so what does multi-party coin toss mean, right, with game theoretic fairness? It turns out actually the definition, there are two natural ways to define it. The first formulation, you can think of it as binary roulette. So essentially imagine every player will bet on either 0 or 1. And then if the bet agrees with the outcome, right, the outcome is either 0 or 1, then the player is declared to be one of the winners. And you can imagine, for instance, the winner wins 1 ether and the loser gets nothing. And then in the second natural formulation, you can imagine this is like an n-party lottery. So we have n parties, we want to elect a single winner at random, and the winner, let's say, will take the entire pot. Okay, so it turns out for these two formulations, the feasibility and infeasibility, the landscape is pretty different. Basically, for the first formulation, which I actually don't have time to cover in this talk, we have a couple other papers that establish a complete characterization of the feasibility and infeasibility. So at a very, very high level, indeed, we can use game theoretic fairness to overcome Cleve's lower bound, but not always. It depends on the parameters. Okay, so in the rest of the talk, I'm going to mainly focus on the second formulation, which is a lottery or leader election. And so again, in this formulation, right, remember we want to elect one winner at random, and the winner is going to take the pot of all bets. And for simplicity, we are actually just going to normalize the utility. It's equivalent to assume that the winner has utility 1, and all the losers don't get anything. Okay, so leader election actually has a lot of applications in decentralized blockchains, right? So for instance, let's say there's a smart contract and it's electing workers to provide some service, like to provide verifiable computation service, and the worker can get some reward in return. So in these cases, like many workers are competing to offer the service because they want to earn some reward in the process. Okay, so before I talk about our protocol, I'm going to actually explain a very simple folklore protocol that solves the problem in log and round. So you'll see. So with this protocol, you'll have something concrete in mind. Here, imagine we have cryptographers and they're trying to elect the next PC chair for the crypto conference. And say they all want to be elected because they're all very eager to serve the community, like even though PC chair is a lot of work. Okay, so they're going to run the following protocol, right? So we pair them up, and each pair will run Blum's coin toss protocol to elect a winner. The winner survives to the next round, and then these people get paired up again, and this goes all the way to the root of the tree, and then the root is declared to be the final winner. And if during the protocol, anyone ever aborts or maybe behaves maliciously, let's say I open the commitment wrongly, which is kind of equivalent to aborting, then the player will just forfeit and the opponent will advance to the next round. Okay, so obviously this protocol will, in general, finish in log n rounds. And it turns out it's not very hard to show that this very simple protocol satisfies a very strong notion of game-theoretic fairness. Specifically, it satisfies two very nice notions. First, no coalition can actually benefit itself. Like no matter how many parties I control in the coalition, I mean, essentially, like the only way for me to misbehave is equivalent to aborting. But if I abort, my guy's just going to forfeit. So basically, your best strategy is kind of just to follow the honest protocol faithfully. And the second nice property is that actually no coalition can harm any specific honest individual. Okay, so the second property is also pretty important because let's say there's a smart contract and it's looking for workers to provide verifiable computation service, right? So maybe I'm one of the big players and I want to monopolize the system by driving away some of the smaller players. So even though like maybe in the short term, it may be, it may cost me something to like drive away the competition, like I'm still interested in harming, let's say, a small individual player. So we want both of these properties. And if like both of these properties are satisfied, then, no matter what your goal is, like whether you're profit seeking, whether you're paranoid and trying to defend yourself against the worst possible scenario, no matter what your goal is, like, your best strategy is always to just follow the honest protocol, which is very nice. And we often say such protocols are incentive compatible. Okay, so because for the case of leader election, like it's very nice that we have a log n round protocol. And the next natural question to ask is, can we actually achieve this in less than log n rounds? Again, we are assuming, there can be majority coalitions and there's no trusted setup. Okay, so this is the question I'm going to focus on for the rest of the talk. But of course, like the first thing we got to try is, why don't we take this tournament tree protocol and directly compress it to 2 rounds? Would this idea work, right? So specifically in the tournament tree protocol, we do commit and then open log n times, but we could alternatively just commit everything up front and open everything all together. But I mean, obviously it turns out this naive approach completely fails. And here's a possible attack. So imagine Shafi and Alessandro, they're in one coalition, and they have a definitive winning strategy as following. So basically, Shafi will commit to 0-0, right? So 0-0 correspond, there are 2 bits corresponding to like each of the 2 rounds in the original tournament tree protocol. And Alessandro will commit to 1-1. And now they wait until the other bracket, the honest bracket, opens their coin. And then they can see, you know, the winner in this case is Dan. Like they can see Dan's second round coin, and then they will make one of them abort. They can choose which one to abort such that they will definitively win. Okay, so this naive idea doesn't work. I mean, which makes the problem much more non-trivial. Okay, so this brings us to our results. Okay, so first we proved that there's a log n lower bound if we impose too strong of a restriction on the protocol design. More specifically, if we let's say we want to be in exactly the same framework as the tournament tree protocol, then log n rounds seem we prove that it's inevitable. More specifically, in the tournament tree protocol is following the commit and then immediately reveal pattern. So if you know your protocol is like players commit in this round and then they open the commitment in next round, then there's not too much you can do. But I want you to think of this lower bound as a sanity check when we design protocols. It's not necessarily a deal breaker, because who says we have to tie our hands and you know strictly follow the paradigm of the tournament tree protocol? Okay. So the good news is that, you know, and this is also our upper bound result. We show that if number one, we are willing to relax the fairness to approximate fairness, and number two, if we are willing to make use of general cryptography, right, not just like commitment and not just like commit and immediately reveal, but we only need standard assumptions. So if with these 2 additional assumptions, we can indeed reduce the round complexity of the protocol. In particular, the round complexity can be as small as log n rounds, and you can see that this is actually an exponential improvement. Okay, so I have to explain what approximate fairness is, and then I'll tell you our protocol. Okay. So let me begin by explaining approximate fairness, right? So essentially, we introduce an epsilon slack. For this talk, I want you to think of epsilon as like 1%, but we can actually set epsilon to be little or 1 in the actual paper. So the protocol is said to be epsilon fair if, let's say, number 1, so PPT stands for probabilistic polynomial time. So if number 1, no polynomially bounded coalition can increase its utility by epsilon, and number 2, no polynomially bounded coalition, and that's 1 minus epsilon fraction in size, at most 1 minus epsilon fraction in size, can reduce any honest individual's utility by an epsilon factor. So if these constraints are satisfied, then we say the protocol is epsilon fair. And also, by the way, whenever I say fair in the rest of the talk, I specifically mean game-theoretic fair. Okay. So that's a very natural relaxation. Like I said, in this talk, we're just going to assume epsilon is like 1% for simplicity. Okay, so this means, note that this means the coalition, right? For the second property, the coalition can be as large as 99%. We can defend even against 99% coalitions. Okay, so our philosophy here again is that we want incentive compatibility, right? So basically we want the honest behavior to be an equilibrium in the sense, you know, if everyone else is behaving honestly, it makes very little sense for the coalition to deviate. You may be able to do just a tiny little better, right? Epsilon better by deviating, but the relative gain is so small that maybe it's just not worth the effort to deviate because there's risk of being caught and exposed. Okay, so in our actual paper, we actually have a stronger solution concept, which is better, but in this talk, I won't have time to explain it. It's called sequential fairness. Okay, if we have time, I can say a few words about it at the end of the talk. Okay, so I've explained the approximate fairness notion. Before I jump into our construction, let me quickly mention our actual result is actually parameterized. So it's like, if R is bigger than some constant times log n, we can have R round protocols that achieve, roughly speaking, 2 to the minus R fairness. So this like this 2 to the R, the term is like pretty sharp in some sense. So as you increase the round complexity, you can get more fairness pretty quickly. Okay, so at a very high level, right, before going into the details of the construction, we make use of extractors, and we also make use of honest majority multi-party computation. So at first sight, our techniques are actually very surprising because we are actually in a setting where there can be majority coalition. So how can honest majority MPC even be useful in such a setting? So you'll see in a little bit. Okay, so let's see how to get this result. Any questions at this point? Okay, I'm going to start with the strawman scheme, and then the strawman scheme suffers from a couple flaws, and then we're going to fix the flaws one by one, and then get our scheme. Okay, so the idea is the following, right? So we have n players, and n is pretty large. We don't want to run the tournament tree protocol among the n players directly. So our idea is to first select a polylog size committee somehow, and then once we do that, we will run the tournament tree protocol among the polylog size committee. And because the committee is polylog size, the protocol, the second step will finish in log n rounds, and then the committee selection will actually just finish in constant number of rounds. Okay, so the key question is, how do we do the committee selection? Okay. So I'm going to describe an approach that I'm going to cheat a little bit. I'm going to assume that there's a random oracle, right? You can think of a random oracle as like, a hash function, like SHA-256. It has good pseudo-randomness properties. Like every time you query the random oracle on a fresh point, you get back a random answer. Of course, when you query the oracle on the same point, it gives you the same answer. So in practice, of course, random oracles, don't really exist. In our final construction, we can replace the random oracle with seeded extractors. Okay, so this idea is actually inspired by proof of stake protocols. So imagine every player is going to post a bit to the blockchain, right? They pick a random bit, and we take the concatenation of all of the bits and feed them into a random oracle, let's say SHA-256. And then we use the outcome to select the committee. So if anyone aborts, then their coin is just treated as a canonical bit 0. Okay, so let's think about what this protocol gives us, right? So imagine in this picture, the shades of red, the red players, they are coalition members. And, if the coalition, like, let's say, wants its own player to get elected, what it needs to do is to increase its representation in the committee, right? Because like the committee is going to run the tournament tree protocol, which is kind of ideal. So what does the coalition have over the honest players, right? What advantage does it have? So one thing it can do is that it can wait until all the honest players post their coins, and then it can decide their coins after having observed the honest coins. So in particular, it can try different combinations of its own coins and find the one that basically helps itself the most. Okay, so as I said, if the coalition wants to increase its chance of getting elected, its best shot is to increase its own representation on the committee. So fortunately, we can prove that an adversary that controls any constant fraction of players cannot increase its representation on the committee noticeably more than its fair share. For example, let's say the coalition controls 99% of the players. In this case, they should have, in expectation, they should have about 99% seats on the committee, and they cannot increase their representation to more than 99.1%. Okay, so how do we show something like this? It's the proof is pretty simple. Like basically, first, for a single random oracle query, by the Chernoff bound, you can show that the probability that the committee is bad is negligibly small, right? Here, a bad committee means there's more than 99.1% red players. So in this case, right, we are assuming the adversary is polynomially bounded, which means it can only make polynomially many random oracle queries. So you can take a union bound over all the random oracle queries, and you basically get that essentially the adversary who controls 99% cannot increase its representation to more than 99.1%, except with negligible probability. So this kind of proof is like, it's kind of like a statistical proof that proves some property about a large enough population. Like it doesn't actually hold if the coalition is very, very small. Let's say the coalition has only 1 or 2 players, then you don't get this kind of statistical property. Like in other words, like the coalition, it's easy to make sure that like 1 specific individual or 2 specific individuals are included, but it's very hard for you to make sure that like many of your players are included at the same time. Okay. So we have good news and bad news. Like the good news is we have essentially proven that if the coalition is sufficiently large, let's say the coalition is more than 1%, like it can be 1%, it can be 99%, then such a coalition cannot benefit itself noticeably. But there are still a couple of flaws with this very simple scheme. The first flaw is that a large coalition can easily harm a single individual, an honest individual. So basically, in order to harm an individual, the coalition can look at all the honest players' coins and try to pick a combination that just excludes the single individual, and they can achieve this with high probability, right? So like the kind of statistical bound we've seen doesn't actually apply to this single individual. So this is bad. And as a second drawback is that the coalition can actually, a small coalition can actually benefit itself significantly. And this is actually pretty surprising at first sight, because I've shown that a large coalition cannot benefit itself noticeably. So now it seems like it's harder to defend against small coalition, right? So this is counterintuitive at first sight. But if you think about it, it actually makes a lot of sense, because like, if you have a large coalition that almost has, let's say, all the players, like you have n-1 players, in this case, your normal utility is already quite high. It's like n-1 over n. So the best you can do is to increase it to 1, right? So like in some sense, here the problem like is actually harder for a smaller committee, a smaller coalition. Okay. So essentially, we just have to overcome these 2 drawbacks one by one, and then we'll have a game theoretically secure protocol. So basically, how can a small coalition help itself, right? It's basically the same attack. It can look at all the honest coins and then decide a combination that helps itself the most. Okay, so let's first fix the first problem. Okay, and then the issue, remember the issue is that a coalition can harm a specific honest individual. And the reason why the coalition is able to do so is because it knows the identity of the individual it wants to harm. So our idea is to basically say, why don't we just hide all the identities from the coalition? So then it will not know who to target. Okay. Specifically, let's say every player doesn't use their real identities in the committee election. Instead, everyone picks a random virtual identity. And this virtual identity is what's actually used in the committee election, but the virtual identity is kept secret at the beginning of the protocol. Okay, so let's say everyone picks a random virtual ID and then they commit to their virtual IDs. So here it's a big envelope, but actually everyone commits to their virtual ID separately. Okay, so once you do that and post the commitment to the blockchain, you then use the same protocol we've seen, right? Everyone posts the random bits and all the bits are fed into the random oracle. You use that to elect a committee, but now the random oracle is actually applied to these virtual identities rather than the real identities. So I mean, of course, at this point, you don't know who are actually in the committee yet because these numbers are virtual IDs, but you can now open this commitment and you can have the reverse mapping and you know who's going to be in the committee. Okay, so this almost solves the problem, except that there's like a little flaw with it, because like here's a possible attack. Like if I control some coalition, I can make all of my coalition members pick the same virtual ID. So put all of my eggs in one basket. And now I just have to make sure that that basket is elected into the committee, and that I can succeed with high probability. Okay, so to prevent this attack, we actually need to modify this idea slightly to say, you know, you are elected into the committee if your virtual ID is selected, and not only so, your virtual ID doesn't have collision with anyone else. So this is kind of to rule out the attack that I've described. In the actual scheme, the virtual ID space has to be quasi-linear, like n polylog n or something. And then if that's the case, like all the analysis will go through. Okay, so this allows us to fix the first problem. And basically the remaining task is just to fix the second problem. So the second problem is a small coalition can actually benefit itself significantly. Okay, so how do we fix this problem? So in fact, I already gave away the solution at the beginning, right? I said, you know, the solution is going to involve like an honest majority MPC, and this is exactly where we need it. So here the idea is like the small committee, the small coalition can help itself because it knows the virtual IDs of its own players. So our idea is to say we make sure the small committee has no idea what's the virtual ID of its own players. And how can we do that? We are going to use an honest majority MPC to choose a masking permutation. And like the MPC is like secure against coalitions that are less than a half, right? Minority coalitions. So if you control less than a half, you have no idea what this masked permutation is. Okay, so more specifically, here the players don't directly choose their own virtual IDs. They choose what we now call an unmasked virtual ID. So they choose this unmasked virtual ID. And then the final virtual ID is formed by applying this masked permutation to the unmasked virtual ID. So again, as I said, the masked permutation is hidden to a small committee in the beginning, and it's only revealed after the committee selection. Okay, so now with this masking permutation and the honest majority MPC, we make sure that the small committee cannot predict their own virtual IDs, and therefore they don't know how to, which virtual IDs to help. Okay, so one thing to note is that the MPC protocol has security only when there's honest majority, but if the coalition is actually large, then the honest majority MPC doesn't give any guarantee at all. So, but in this case, it's still okay because like our the first part of the construction and the analysis we saw, like already secures against a large coalition. Like you cannot simultaneously make sure many of your players land in the committee. So it's still fine with the large coalitions. Okay. So I won't prove the approximate fairness formulate. Essentially with this, we've overcome these two drawbacks, and to get our final protocol, we are just left with one problem, like how do we remove this random oracle assumption? I think, I mean, in the interest of time, I won't go into the details here. So at a very high level, we are going to replace random oracle with the combinatorial object called seeded extractor, or it's also called a sampler. But it's like, it's more complicated than it originally seems. Just to quickly summarize, if you want to replace the random oracle with the seeded extractor, you have to do a two-phase committee election, right? So what we actually do in the final protocol is we first run Figus lattice beam protocol, but only run a single iteration, and we use that to elect a preliminary committee. And this preliminary committee election phase only satisfies some really weak properties. And once we have the preliminary committee, the preliminary committee will run something like the random oracle-based protocol to elect the final committee, except that now we don't use random oracle anymore. We just replace random oracle with like a seeded extractor. And then finally, the final committee will run the tournament tree protocol to elect the final winner. Okay, so that's the final construction. And I'm just going to refer you to the paper for more detailed proofs and formal definitions. Okay, so before I end, I just want to say a few quick words about this stronger notion of fairness, which we actually use in the paper, right? So I actually cheated a little bit with the fairness notion I told you. In fact, in practice, you want something stronger, like with this kind of epsilon fairness. Let's say, you know, one property we want is that no coalition should be able to increase its utility by epsilon. But there can be like some kind of contrived, like some bad protocols can still satisfy this notion, right? Which means like this is not the most desirable solution concept, right? So imagine there's a contrived protocol and with some small probability, epsilon over 2, some bad event happens. Let's say the player Alice somehow discovers the password of Bob. And if this bad event happens, Alice will be strongly incentivized to deviate. Because in this case, maybe Alice should just steal all of Bob's Bitcoins. But otherwise, if this bad event doesn't happen, then let's say the players are incentivized to behave honestly. So such a protocol can still satisfy this kind of epsilon fairness. So the actual notion we use in the paper at very high level says that, you know, we want to make sure that except with negligible probability, at no point during the execution should the coalition have epsilon incentive to deviate. Okay, so please see the paper for the more detailed definition. There's actually some technicalities in the definition because like it involves computationally bounded players. Okay, so earlier there was a line of work that focused on you know, the intersection of game theory and crypto. Like for instance, there's a line of work on the so-called rational protocol design. Our non-sequential notion of fairness is somewhat equivalent to a multiplicative variant of their notion, but our sequential notion is stronger. And we also discovered like the approximate fairness notion used in some earlier works, like fruit chain, is not strong enough. Like, you know, we think the sequential fairness notion is the right approximate fairness notion. Okay. So to conclude, I want to mention that like in decentralized blockchains, right, there are lots of exciting problems where you need something like game theory, economics, and crypto. So this is a very exciting playground, in my opinion. And you know, in this area, what's interesting is like the blockchain projects are kind of ahead of research. Like they're already deploying protocols with game-theoretic fairness, and we are just trying to catch up and try to understand, like formally analyze these protocols. And oftentimes, like interesting thing is like oftentimes we don't even understand how to formulate the problem. So I think we need a new scientific foundation here. So thank you very much.